Yeah.
Um,
Yes, sir.
I have to make this one quite brief, but I was just reading in chapter 13,
Yep.
and in chapter 13.1, that
Uh-huh.
table with the values,
Yes.
what is that? I'm having trouble figuring out what those values actually represent.
Those values represent the amount of energy required to start the rotation of a proton in a nucleus of a hydrogen atom going from one orientation, one direction of spin to the other direction. So you're flipping the direction of the spin, and that is the reference to the word resonance. So it's not the normal resonance you learned about when you learned about resonating electrons. Remember, the word resonance is not strictly for chemistry. We hear about people with resonant voices, right? I'll do my best. I'm not. I am the opposite of a person with a resonant voice, but James Earl Jones, use the force, Luke, has a very resonant voice. What does that mean? Well, it means his voice waves have a large amplitude, going up and down, oscillating up and down. So the concept of resonance in general is talking about going from one extreme to another. And with electrons resonating in a structure, you're talking about them flowing in one direction to one side of the structure, and then in the other resonance form, they flow to the other extreme. And in resonance with nuclear magnetic resonance, we're talking about the spinning proton being caused to resonate from clockwise to counterclockwise or vice versa when it's presented with the correct amount of energy. And the table you're talking about, I'm going to bring up right now. We'll briefly take a boo at it. If we look at
So,
any of our, sorry, go ahead.
um,
Mm-hmm.
so that value represents an amount of energy required to flip the spin. Essentially, is what you're saying?
Correct. That's exactly what that table represents. So looking at any old test one, we're going to see if it opens, and it might be opening somewhere where I don't know about it, and I think it did. There's our table of content. There we go. So I assume I have your permission to use your first name. I don't want to say it until you do
You
give it
may.
to me. Yeah, Devin has asked me about this table, and what we can get from it is one, we can predict where we should see a peak in an NMR spectrum based on the type of hydrogen in the molecule. So if you're looking at a normal methyl group, which is very common in organic chemistry, attached to some kind of carbon chain, you would expect to see a peak at this low energy. That's where it would start to resonate. Whereas if you put more electron withdrawing atoms like a bromine on the carbon that has the hydrogen, I'm over here now, it takes a lot more energy to cause the resonance because the bromine pulls electrons away from the hydrogen. And you probably read the word de-shielding in the textbook. And that's what electron
Is that
withdrawing
the
groups do.
inductive effect you speak of? Like
Yeah, the
electron?
inductive effect of an electronegative atom will pull electrons away from a hydrogen, and that means it feels more of the magnetic field because electrons are what block the magnetic field. So with an electron withdrawing atom like bromine, there's less blocking. So the gap between the two energy states is larger if there's an electronegative atom around. And that gap is, these energies represent how big that gap is. The biggest gap would be here. This is a very positive hydrogen. It doesn't feel the electrons in that bond very much because this thing wants to become, a carboxylate and a proton. So that's the highest number we got. And the ones where the electrons are closest to the hydrogens, this atom here, silicon, is even lower in electronegativity than carbon, isn't it? So that pushes electrons towards these H's, and that's what sets our machine at zero. This tetramethylsilane, it's a standard molecule. So yeah, these values, you don't memorize them. They will be given to you so you can use them on the test. and they help you predict where the peak should be. And the more powerful use of this table is when I give you data and I tell you there's a peak at 3.5, and I tell you the formula of the molecule, and in that formula you see a nitrogen. You say, oh, what could be at 3.5 in a molecule with a nitrogen? I'm thinking. And then you say, oh, there's a nitrogen on a carbon, and that hydrogen that's on that carbon that also has the nitrogen would be around 3.5. So it's useful information, isn't it? NMR is the most powerful tool in analytical organic chemistry. It changed organic chemistry forever when they developed this technique. It's really just physics. It's not organic chemistry at all. We use the physics, we stand on their shoulders, and we figure out our molecule structure within minutes instead of days. Anyway, long-winded answer.
Physics.
Sorry. Yeah. Yeah, it's all about physics when you're talking about spins and going back and forth. Yeah.
Right. A lot of new terminology.
Yeah, it is. It's a chapter that students like, and we don't have new organic chemistry in there, so we're not adding to our mandatory list of reactions we have to memorize, etc. It's a good break, but it's its own thing that has to be learned, and you will see NMR questions on every test until the end. So you're not learning it just for this test. Your goal is to be able to do a problem like the ones on the ends of these exams. These are the hard ones. No, not that we skipped that. No molecular recognition during COVID. Hold your applause. What we have here is this is where NMR's power is seen. The data here, coupled with a few facts, allows you to be able to predict the structure of this molecule. But don't start with this kind of question. Start with the previous question here. And you got to do this. You got to answer the 3 questions for every hydrogen in a molecule. Delta is where's the peak? Multiplicity is what pattern is the peak? And number of hydrogens is how many hydrogens are in the peak. So read about those, do all the practice problems that look like this, and then hopefully, maybe tomorrow's Q&A even, somebody will get to a point where they're comfortable enough and they want me to try one of these. I don't know if we're at that point today, but we'll see how it goes. So
hello, Dr.